Hello, welcome to our pre-recorded talk on proposals to improve CAFA evaluation based on community participation. My name is Jeffrey Eunice. I'm a volunteer scientist at a new nonprofit, Eunice Aging. This work is a collaboration with Dr. Zhang at Yale and Dr. Turunen at the University of Helsinki. Protein function prediction is among the most important problems in bioinformatics. The problem is especially challenging due in part to the large number of sequences, the imbalanced classes, incomplete labels, structured outputs, and experimental bias. Obviously, issues like not knowing true and complete protein functions affect evaluation as well. Some of the components for an AFP evaluation include a way to compare predicted functions P to the correct functions T, which is complicated by the structure of Go and the annotation bias, a way to average evaluation scores over proteins, and we have to consider which targets do we want to evaluate, and should all proteins be weighted equally, and also baselines to facilitate interpretation. How do we compare P to T for a single protein? In a standard multi-classification problem, we could just ask if our prediction cat equals the true class cat. Protein functions, however, are expressed as sets of Go terms, and there are almost 50,000 Go terms to choose from. Furthermore, the ground truth T is incomplete and ever-changing, so the predictions are trying to hit a moving target. Therefore, an alternative is to inspect P and T and count the number of terms in their intersection. A problem with this approach is that not all Go terms are equally informative. Predicting that a term does binding is easier than predicting that a term is a cis-trans isomerase. To address this issue, let me give some background on information content, defined as the negative log probability of an event. For example, the information content gained when observing the outcome of a fair coin is the negative log of 1/2, or 1 bit. Learning the outcome of a certain event adds no new information. The information content also has nice properties that you would expect, including that the information learned from observing independent events is additive, and observing events never decreases information. We'll be using the conditional information content, which is the information content of observing an event X, given we already know something else Y. Applying the definitions of information content and conditional probability, you can see that we can calculate either as the log ratio of these probabilities, or intuitively as the total information content minus the information content of the stuff we already knew Y. When applied to Go, we see that the information content of molecular function is 0 because all proteins are annotated with this term. To calculate the conditional probability of peptidyl prolyl cis-trans isomerase, given that we already know the protein is a cis-trans isomerase, we can either use the intuitive definition derived on the previous slide, the cumulative IC minus the IC of the parent, or using the negative log ratio. Interestingly, we see here that this specific term, given that we already know it has the parent function, is relatively uninformative, since that's the case over 80% of the time. So, if we replace 1 when counting true positives with the information content of each true positive term, we get a score that accounts for differences in terms. I've been showing how to weight true positives by information content, but you can also do this for other performance metrics like false negatives, precision, and Fmax. IC-based performance metrics are very effective at separating signal from noise. The gray dashed line is the naive baseline, which just predicts Go terms according to their background distribution. The other two curves are legitimate predictors. According to precision recall on the left, naive appears to be an effective predictor, and it is, at predicting the most common terms. On the right, however, the information content-weighted version of precision and recall makes it clear that naive can't actually make informative predictions for molecular function. I would say that precision, recall, and Fmax, which attempts to summarize the precision recall plot in a single number, are the primary performance metrics used in CAFA and in publications. None of these use the information content. There are a number of better alternatives. One that is in practice is the semantic distance, based on the information content-based metrics, remaining uncertainty, and misinformation. So far, we've only discussed how to score T and P for a single protein and implicitly average them over all proteins in the evaluation set to come up with an overall score for the method. We're dealing with an open world where Go terms that are not annotated to a protein nevertheless may be true. Because of experimental bias, some proteins in the evaluation set may be well studied and have numerous annotations to specific Go terms, while a large number of other proteins may only have very shallow annotations, perhaps due to a high throughput experiment that assays one functional aspect of each protein in an organism. In many cases, we know that a protein must have a function more specific than what is experimentally determined, and it seems unjust to penalize methods for making predictions that are consistent with, but more specific than, the experimental annotation. I'm not sure we're ever going to solve the challenge of having to evaluate against an incomplete ground truth. However, we can ameliorate its effect by using a weighted average instead. If we weight the per protein evaluation scores by the information content of the ground truth, as proposed by Dr. Clark and Dr. Radivets, then it will naturally downweight proteins with less informative annotations. I think one reason why this performance metric is not more widely used is because it's more complicated to implement. Personally, I'd like to see a project that creates a library for AFP that provides a suite of evaluation metrics and components. CAFA is run as follows. Predictions must be submitted by T0, and new experimental annotations are collected until T1, and these form the basis for the set of proteins being evaluated. 3 types of targets are defined. Targets that lack annotation on T0 and gain new annotation by T1 are called no-knowledge targets. Targets that have annotations at T0 and gain new annotations on a different previously unannotated ontology by T1 are called limited knowledge targets. And targets that have annotations on T0 and gain additional annotations on the same ontology by T1 are called prior knowledge targets. Ideally, we want to evaluate predictions for all proteins with a new experimental annotation. If that is unfeasible, the set of evaluation proteins should be representative of the proteins with new experimental work. CAFA assumes that it is indeed unfeasible. After all, there are 200 million proteins in UniProt. Therefore, the organizers first pre-select around 100,000 Swissprot proteins from the reference proteome of several model organisms. There are a few issues with the current method for target selection. First of all, the set of targets is not representative of the set of proteins with experimental work. In this case, new experimental annotations came from 387 species, but CAFA would have only evaluated 15 species. In particular, we noticed that 74% of the targets evaluated in CAFA2 were from human and mouse. Experimental biases mean that most experimental annotations are from model organisms, but CAFA target selection gives them undue influence in our evaluation by excluding most non-model organisms. A second issue is due to excluding proteins from evaluation with too much or too little evidence. No-knowledge targets and limited knowledge targets are evaluated separately, and limited knowledge performance results are in the supplemental material. Prior knowledge proteins are excluded, but they make up the bulk of experimental work. On the other hand, CAFA targets are selected from Swissprot, a database of manually curated proteins. If the goal is to see how well AFP works on proteins with no prior knowledge, Swissprot seems like a strange choice of target proteins. Taken together, you can see that the primary mode of evaluation, no-knowledge targets from select species, considers only 7% of the total targets had we considered all proteins with new experimental annotations. Town hall participants made several creative suggestions that would achieve a more representative set of targets. One approach was to have participants predict on all of UniProt. The size of the dataset would most likely require teams to develop multi-scale methods that predict on the bulk of proteins with a simpler method, or the organizers could automatically supplement submissions with baseline predictions. But we propose an alternative submission format. Participants could submit sandboxed prediction methods, perhaps in a containerized format such as a Docker image. This would avoid having participants waste resources making predictions on targets that are never evaluated, while ensuring that they don't have access to information after T0, and would increase reproducibility. In fact, this is the main submission format for most of the DREAM challenges. What should we consider to be the ground truth? Currently, we consider low-throughput experimental Go terms plus author and curator statements. However, there exist high-throughput experimental evidence codes, which includes things like high-throughput direct assay. Protein functions predicted and confirmed by high-throughput direct assay are scored as wrong. Additionally, proteins with high-throughput experimental evidence are still eligible as no-knowledge targets. We think that all experimental determined annotations should be included in the ground truth. First of all, by definition, they are experimentally characterized. Second, error rates can be estimated by counting annotations rejected with a not annotation or eventually confirmed by a new experimental annotation. And error rates for high-throughput direct assay annotations are close to zero. High-throughput annotations might be for Go terms that are more general than those from low-throughput experiments, but application of our information content-based metrics alleviates that concern. One thing that seems odd to consider is whether we should consider any electronic annotations as the ground truth. Please consider the example of the RISC protein. RISC was first isolated in 1964. It was incorporated into the manually curated Swissprot in 1988 as an iron-sulfur protein, and manually assigned the keyword for 2-iron, 2-sulfur in 2002 based on extensive experimental evidence. In 2009, these keywords were mapped using manually constructed keyword mappings. However, since these mappings are applied automatically, the RISC protein has an IEA annotation for 2-iron, for 2-sulfur binding, and many other Go terms to this day. Even if we decide not to incorporate this type of evidence in the ground truth, I think we should have baselines that use these annotations and all other information available in the training data. Although the evaluation metrics are straightforward, it's hard to appreciate the numerical values they provide, since they depend on the datasets and method being used. A baseline is a method that helps interpret the evaluation data, and therefore tend to be simple, well-understood methods. For example, the naive baseline shows how well a method can make predictions only by exploiting the unbalanced class info. It does this by ignoring the query protein sequence entirely and predicting every protein has Go term G with probability equal to the frequency of G in the training dataset. The BLAST baseline is another baseline implemented by CAFA. It predicts Go terms based on maximum local sequence identity among templates detected by a default BLAST run. The use of local identity is problematic for BLAST because the score can be very high even if only a tiny portion of the sequence is aligned between the target and a very low-ranking template. Therefore, we evaluated simple modifications of this baseline. We implemented two baselines based on sequence identity and normalized bit score, both of which performed better than BLAST using local ID. We also implemented a baseline that predicts Go terms with a probability equal to the frequency of each term among the BLAST hits. This is a lot like naive, except the universe of proteins in naive is replaced with the proteins found by BLAST. As we might expect, this method does quite well. On the CAFA 3 dataset, BLAST using frequency outperforms these other baselines, according to Fmax and SMIN, without changing any of the arguments to BLAST. At our poster, Chen Xin will discuss other ideas and experiments related to baselines, such as frequency weighted by bit score, and methods that incorporate the electronic annotations that are available in the training data. We acknowledge and thank the participants of the CAFA Town Hall held earlier this year. We also thank the CAFA organizers, Dr. Radivets and Dr. Friedberg, for being open to suggestions, and I thank the other authors for making this work possible. There are many more exciting ideas in this field. Please contact us by email if you're interested in working together. Thank you.